welcome back to the computer vision online video lectures. We are now moving to a different topic now from what we discussed so far. This is like motion estimation is the application for which we would start with. And then again, we go into theory, of course, whatever is required for estimating the motion. That's what, of course, we would be doing. And let's start with an introduction to what it means by motion estimation and why do we require that. Again, as usual, my most of the content is adapted from Professor Aaron Bobbick's video lectures on Introduction to Computer Vision course available in Audacity. And again, he has adapted slides from various other sources, including the one I mentioned there from the textbook and few other sources. So this is a kind of, I don't own the rights for most of the slides. Now, you might have already sensed that the moment I'm saying motion estimation, it's not just about one image. There are multiple sequence of images, and from one image to the other image, how much of a motion is there? How much of a movement is there? That's what we are going to compute, or in other words, perhaps we are going to look at some of the methods that help us to estimate the velocities or displacements. Both are related, although not same, from a given sequence of images. That's what we are going to look at. So as it should be clear to you by this time, now we are moving from a 2D image to a set of 2D images, or more appropriately, a sequence of 2D images, which are at different time intervals you are taking it. Let's say you here, for example, maybe a scene you are capturing a video, so it doesn't require much of an introduction for all of you. You are quite aware of a video versus an image. Essentially, a video is nothing but a sequence of images with a time gap. Even that's how our brain interprets things. We know we still capture things in frames, but the distance between the frames is something that makes it appear continuous. So essentially, video is nothing but you have a sequence of images. And here T, you could refer it to as the frame number. Of course, then if you know the frame rate, you could always relate it to the time instance at which it has been captured. But for our presentation and for this course, when I say here T, you consider it as the time frame at T. It's a number essentially, the teeth frame, not the teeth, but the teeth frame number T, and then t plus 1, t plus 2, t plus 3. Those are the frames. Of course, if you know, as I said, the frame rate at which you captured a sequence, you could always correlate it with at what value of time it has been captured, and in terms of time, what is the interval. Well, before doing any of the going into any of these methods, let's first see some applications where perhaps this could have some utility. Okay, can you I would like to, given that image, can you make an inference, or can you make a guess on what could be perhaps an application where you could use this motion segmentation?
Yeah, someone said animation, sir. So
Yeah,
it's like
okay. Any other?
if
Mm,
also in detecting automatic door sliding, like if
mm,
we go near that and the door
right.
moves.
Yeah, okay. From these images, can you think of what is perhaps this application is about? What could be the application about?
In the field of gaming, maybe.
Hmm. Yes, that's something you could use. Very good. If you are using something like Xconnect or Xbox is there, you are making some gestures there and you want to interpret the gestures, right? So you need to separate the background from the foreground, right? And you could assume in a lot of scenarios where your background is stable and it's you who are moving. So once you look at different frames and see what is it that is moving. Okay. And of course there can be always exceptions, and you could come up with models that could address those exceptions, but in general we are talking about. So that's one application where in a gaming Xbox like kind of stuff where you play games, that can be done. Okay. Another thing you could think of is you want to you want to create an augmented reality where the person is still there, you want to change the entire background. So that's where you figure out what is it that is moving coherently, and so that the rest of the objects, maybe even despite moving it, you could identify them, and still you could replace them if required and do whatever is required. So augmented reality, you want to do something, you could do it. Then another thing is you want to interpret what he is saying through his gestures, let's say. So there also you want to extract this guy, and then you could make and then an inference. You could, on top of it, you could come up with some other algorithm that makes an interpretation of what he is saying. Or another application I could tell you is you want to make a conversion from speech to text. Okay, then for example, consider the same video. There you need to track my lips there. So something which is moving here, the lip movement you need to capture. So that's something where, and depending on how they are moving, and depending on each word that we pronounce has a sequence of lip movements. It's not just a very simple case. So that's where perhaps motion estimation could help you. Another thing, for example, a simple one could be, there are some old videos with you where my speech, let's say, is not in sync with my gestures or with my lip movement. Okay, this is something we see in quite a few scenarios while we are watching some movies which are not very professionally recorded, or some ripped versions of the original one. You would see the sync missing. So for example, then uh, this is some aside, yeah, very not so common application, but just to say something, I'm saying this can also be done, right? Then another application you could see here is uh, let's say in a movie you want to see where a sudden transition of scene has happened, for example, right? So then if you figure out which are the objects that are moving and where they are moving, and for example at this shot you will see there is a sudden change here, disappearance. So if you are like trying to map this person to this person in the next frame of or sequence of images, you would see some motion, but suddenly you will see going things suddenly disappearing, or suddenly the values becoming quite a high or untractable there, intractable there. So then you would say shot boundaries where they are there. Suppose for some reason you want to separate those shots. So that's something you could do here. And well, I remember one of the student earlier doing another nice interesting application of this motion estimation, I think 2 years back, I think, if I'm not wrong. That was about keyframe extraction in a given classroom video. So for example, I'd be writing on the board, so he want to automatically extract the notes out of it. A video has been captured, I have not given you any slides, everything I am writing on the board. So you could see a sudden, you could expect a sudden change when means there is a gradual change while I am writing, and when I erased something, or doing some, or I moved completely from the board and it has, the video has moved to articulation through gestures rather than writing on the board. That's where you want to capture something. So he was doing something like this using that's referred to as keyframe extraction. Similar, you could think of quite a lot of applications like that. And here again, those are there are many, just we are trying to sample and get a feel of what kind of applications could be there. You consider now, for example, you are capturing the video of traffic on a road, on a national highway. A lot of cars are moving there, and you want to keep track of those cars for various reasons. Maybe you want to count the number of cars, maybe you want to look at with what speed they are going, and if there is any violations there, or if some abnormal activity is going on, or if there is an accident happened, automatically you want to analyze the video and say something. So there, each one would be moving coherently, each object in some with some velocity. So that value could be constant, for example, for a given object there, but there are different objects moving in different directions, or with different, if not in different directions, with different displacement values or velocities. So that's something you could do once you do the motion estimation. Another example is even in segmentation. You just might want to do a segmentation, but in certain scenarios where the segmentation problem turns out to be very challenging, so then having a video, if you are having a video of the scene, that might help you. For example, you could see here a picture. I don't have a video for it, but I grabbed it again, I think from Professor Aaron Bobbick's lectures. One screenshot of that is where you have a mongoose and the snake, and the background is also pretty much similar to those two objects, if you consider those two as object one and object two. And if you simply use some textural information, or if you simply use some edge information, that won't be good enough to get a very accurate segmentation or a very good segmentation of those two objects. On the other hand, if you have a video of it and see which are the objects that have a coherent displacement, and based on if you are additionally using that information, you could perhaps arrive at a better segmentation. So that's another application where you could use it in segmenting the objects itself on a given image, but where you could explicitly exploit the information of motion in order to get a much better segmentation than using a static frame. Another one is similar to the panoramic view. This here it is referred to as mosaicing. Your field of view of your camera is limited. You have taken multiple pictures, right? And then even if you notice here, situation is made more complicated where there are moving objects as well. So once you know the motion estimation, so with the delay that you are taking the next image, this object might have moved from that. So if you could estimate that and come up with a very good model for it, from all these images you could construct something like this, where a simple panoramic view based stitching of finding out the key points, a simple model might not be enough here to get this, because it is like you are taking a panoramic view, but in that the objects are moving. So in that case, of course, you need to have an estimation of motion of the objects, and then only you could avoid the blur and do it's of course this model, it cannot be a simple model, that requires a lot of parameters to be taken into account, but in principle it is definitely much, you would arrive at much better results if you can do a motion estimation and incorporate that in your process of mosaicing or panoramic view, particularly when the objects in each of your individual images are moving. So that's another example that you could think of. Okay, this is a very tailor-made example, particularly made customized example to show that you in fact motion estimation would improve your segmentation. Hope the animation you are all able to see there. There is an object here. This is a synthetic example where your object is from one frame to the other frame, it is moving. There is no way you use edge detection, you use textural information, you use key points, whatever you want to use, unless this example has been designed in such a way that unless you make use of the motion value, you won't be able to segment that moving square which we consider as an object. Okay, hope you are all able to see that that animated GIF, right? Hope you are not just seeing the segmented one. Is it visible to you guys on the screen?
Yes, sir.
Okay, good. Oh, so these are by no means an exhaustive list. This could be, there are quite a lot of other applications. For example, segmentation of objects in space you have seen, and segmentation of objects over time is also something else you could think of. See, when you are assuming that the frame rate is good enough and to capture the object in within the next frame, not moved very far from the earlier position. So there are quite a lot of models that where you segment the object in one frame, and in the subsequent frame you would use it as an initialization for the next coming frame, and from there your model would evolve and get, for example, you are looking at edges. Okay, we will hopefully will have some time to discuss some of those segmentation methods where you have an initialization, and from there you evolve your initialized curve in order to get a good segmentation. So though that is where you could make an explicit use of motion, or you might model the dynamic motion of that object itself. That can be done. And another thing is estimating the 3D structure. So in order to estimate the 3D structure, your camera might be moving, if not your yeah, if not your structure or object for which you want to extract 3D. So there also you have to model and estimate the motion in order to reconstruct the 3D object. We'll anyway come back to that after some time, after some classes. We will yeah, get into that. And then learning dynamic models, how they are moving. Okay, hope that is should be already clear by now to you, that there also motion estimation is required. And recognizing events and activities. So if there is any abnormal activity is there, suppose if all people, you have a camera that is recording in a crowded area where people are moving in all directions, and now you suddenly see that all people gathered at one spot. So it's very likely some accident might have happened, or something unexpected would have happened. And now if you want to automatically figure it out and raise an alarm, so that is where you need to again make an estimation of motion of the objects. Your algorithm has to make use of that information. So that's something you could think of. Another application you could think of is improving the video quality. So while you are capturing the image, suppose there is a jerk going on here, or the object itself has moved, or your camera has moved. So if you could estimate its motion, you could stabilize that and get a much better video. So this again is a very important thing even in the medical imaging, where for example you are acquiring an MR image of a fetus MR image in the mother's womb, or some child who is moving quite a lot, or even an adult who cannot remain stable for some because of some health conditions where there is a lot of movement. Because of that, since you would be capturing a sequence of images, and from that you would be constructing the image, so you need to there figure out the estimate the motion that has happened and compensate for it in order to improve the video quality. So these are the some applications that you could think of. Now let's take a look at what are the type of methods that you could use for estimation of the motion. This can be classified into two categories. One is feature based methods, and second one is direct dense methods. Feature based methods are something that we have already seen so far. For example, you extract features, you now describe those features, and then you for example you use a Harris corner detector to extract some key features in a given image. Similarly, you run it on the subsequent frame in your video, and you extract the features there. And then now you have all the tools to do it. By this time you are already equipped with the tools for doing this. You use Harris corner detector, then let's say you use Sift in order to describe them and find out the matches. Okay, and after that you do, for example, transformation. You compute the transformations which you studied, let's say affine transform or a rigid transform, depending on what exactly you are looking at it. And then maybe you are having more key points than required, so you use ransack and get the estimation for it. Okay, these kinds of things you could think of. But again, what could be the problem? Just since I just mentioned the name of ransack, I am just posing this question: what could be the problem of using ransack? In did you see any problem in any of the applications that we discussed so far, if at all you are using ransack for parameter estimation?
I think when we have multiple moving objects, then it will be difficult
Right.
to track.
That's right. You are drawing multiple samples, but if those samples correspond to different objects, which are by different objects, which are moving with different velocities or display having different displacements, ransack doesn't work there. So we left it as an open problem at that point of time. And The second class of methods would address this issue, which is a direct dense method, which directly recovers the image motion at each pixel level. So this is a pixel based approach. At each pixel, you would look at where it has moved. And we call them as a dense motion fields because you have it at every pixel. So if you have a 100 by 100 image, you have 10,000 displacement vectors you are getting. Okay, each one can have a moment in x and as well as in y. So unlike the key points which are sparse, if you are estimating the motion at each pixel, that is pixel wise estimation of this motion, then these methods are referred to as dense methods or direct methods, because you are right away directly using pixel intensities to estimate the motion. Feature based methods usually are applied when your image motion is large, because while you are computing the feature points, there might be already some amount of disparity, like it might be plus or minus few pixels is where you could get it for various reasons. And well, good enough like context about that already from the good enough information about that from your previous lectures, from our previous lectures. So if it is order of some tens of pixels is what the displacement you are expecting from one image to the other. Okay, by the way, if you are not using ransack, there will be some other set of applications which could perhaps take into account the scenarios where there are multiple objects that are moving at their own displacements. Okay, it is not as such a drawback of feature based methods, but there you have to model it in such a way that you cannot simply randomly pick all the some points there, but you need to come up with a different strategies. Yeah, that's all. It's not the, just keep it in mind that that's not the drawback of feature based methods. It's just the drawback of ransack, that's all. Okay, so if the displacements from one frame to the other are not so high, which is order of very few pixels, maybe 2-3 pixels or so, that's when you go for direct dense methods. By this time we have discussed enough about this first category of methods, since you have already seen all those list of extracting the feature points, describing the feature points, computing the transformation, and then further fine tuning the transformation based on methods like ransack. Okay, that whole pipeline you are very familiar with by this time. So it is now the second class of direct dense methods that we are going to see in this class, next class, and maybe next week also we'll be going through these methods. And these are the particular uh, specific methods that we refer here, are also, or we are going to study here, is referred to as optical flow. That's also, it is something that is referred to here. So here you assume the optical flow is the apparent motion of object or surfaces. So when you are looking at the pixel based movement, not always this is going to represent you the motion. Why is it so? Well, if you are, let's say your assumption here is you have pixel set of pixels here. Okay, for the convenience I am putting each pixel intensity instead of using different intensities. Assume that each intensity level is represented with one color here. First frame I of x y comma t, second frame t, next frame, so this is tth frame and this is t plus 1th frame. Now the goal is, in optical flow what it tells you is how much should I move this pixel such that it maps with this in the next subsequent frame. So I need to find out x plus u, the displacement in the x direction that I need to make, the displacement in the y direction I need to make. These are the two things I would find out such that the first frame matches with the pixel intensities in the first frame would match with the pixel intensities in the second frame by moving these pixels. Okay, so now let me come back here. You could see here it still retains some of the drawbacks or issues or challenges that we have in key point detection and key point based approaches. One being, for example, here you consider that image as there is some base, okay, which is moving there. Okay, that's moving, that's the table, you could think of it, which is moving. Okay, I don't know whether it's a cake or it's just a simple object that is moving, I have no clue. But for the time being, let's assume that there is a base which is moving on that. So there is a Rubik's cube there. Now the idea is you want to see where this has moved. Now now think of this approach that you are doing here. By the way, if you have noticed here, this and this are having same color, which means they are of same intensity, but optical flow would look locally there. So this is would eventually would map the, you move in this much of distance here, so this x and this y would end up here, and it will not try to match it with something here because it is looking locally. That's why we are saying the displacement in pixels is subpixel or at most a few pixels. Okay, anyways, coming back here, so you could see here there is no way for us to map the pixels in this uniform region because there is no intensity. That's a uniform region with the same intensity values, so you cannot find out a mapping there despite that moving. So you still have, in fact, all the kinds of challenges that we face while we are doing with key points, that is coming from the very nature and characteristic of the image itself. We ourselves, if we are putting our focus here, there is no way you could figure out that it has moved unless there is a textural variation. And then there are regions where you could observe emotion, right? For example, there is a pattern here in the peripheral region of that rotating table or whatever you call it, and there is in fact some pattern here where at least these angles would be varying. So that's where you could observe some movement there, and then you could try to map it to the corresponding ones. And now the arrows here are showing you from this image how much a given pixel has moved. So you could think of it again in terms of this, where you are trying to find out in the a nearby pixel which is having the same intensity as the current pixel. And now just like you are drawing arrows here where there is an orientation and how much it is there, that magnitude is also. See this, for example, you move here, hope my pen is here. So yeah, so hope you have to move in the x direction this much and y direction this much. So that's telling you that story once I give you that arrow. Now, any observations from this image? Right, because of uniform intensity in optical flow, it results as if that region is not moving at all. Right, good. That's observation number one. Very good. I want to see at least couple of more observations.
Means it shows this which object has moved in which direction.
Correct. That's right. Good. So it is roughly telling you in which direction you could figure out. Okay, right? But I want a more subtle point here that I want you to notice.
The magnitude of displacement vectors is different for the outer periphery. You called it the base, or and the Rubik cube if we compare.
Excellent. Very good. That's what I was expecting, the observation from you guys. Now tell me why. Now the question, the observation, now you try to justify your observation and what perhaps is resulting in this.
In a sense, it's giving us the information of the distance from the camera.
Very good. So can you be more precise? Can you be more
Uh,
specific?
if the object is closer to the camera, then the displacement vectors are larger than if they are farther away.
Very good. Very good. So that is why now the statement should make sense to you. Optical flow is the apparent motion of the objects or surfaces. So don't forget that it's not the 2D object that is moving. It's a 3D object that is moving. Since it is a 3D object, based on how far it is from the camera, what you could get is only an apparent motion. Okay, we are got used to it, and in fact that is the cue that we use to assess even from a video which is close to us and which is far there, to make an assessment of the height information or a three-dimensional information. We use this cue inherently or not inherently. We'll have some interesting discussion about it in later classes. This is what we have been trained. Okay, not explicitly, but that's what, as once we are born and we start seeing things, this is how, this is not something there inherently. It is not something that comes as an installed version. Okay, this is something you build, or each of us build over a period of time, where depending on the apparent motion, we in fact make an interpretation of the 3D information. Anyway, we will come and we will in fact discuss more exciting things about that in later classes after some few weeks, but that's a very important observation. And keep in mind now for the rest of the classes on optical flow that although we started with the estimation of motion, what we would be interested is to, we are happy for the time being with computation of an apparent motion. Is that point clear? You could see here the cube is, Rubik cube is farther than here. Of course, this we also interpret based on where it is located in the, how do we interpret 3D is a very nice, very intriguing question. So one of them being this apparent motion when you are seeing it. There are other things where the object is located in the image is also another thing. I would stop the discussion about how we interpret 3D there, just not to spoil the upcoming discussions about that. But for time now, for the time being, that's good enough. Okay, so you could see by optical flow, the message here is we are going to compute the apparent motion. This word apparent here has a very significant and profound implications here. That's what I want you to make a note of it. Okay, so this is what we would like to compute.
Excuse me, sir. I have a
Yeah.
question.
Yes, please. Yes, please.
So we talked about that we'll have no optical flow vectors in uniform intensity regions,
Mm,
and at every pixel we look around the neighborhood to compute the
correct.
corresponding
Correct.
movement. So what is the size of the neighborhood in which it took? Like my question is, on the top of the Rubik's cube, I see a very small square,
Mm,
and I see that square as a uniform intensity region of that
right.
size.
Right.
But in corresponding motion flow vector, I can see the all the flow vectors.
Right. Good. So that's a very important aspect of this optical flow is what is the neighborhood that you would consider. Okay, there are different ways. So since we already discussed in Harris corner detector the scale invariant, so where you are looking at different scales, there is something called as hierarchical Lucas and Canada. I will come to that a little later, where there are ways by which even if you could even if it is expected to give you results when the movement is only few pixels, there are ways you could make it work even when the motion is more than that. In other words, that is how you would expand the neighborhood, to put it in terms of what you asked. So that there are ways you could increase the neighborhood. Okay, so that's what we would discuss in the upcoming week. First of all, what we would like to do, a technical term, let's talk with the term. They refer to it as brightness constancy constraint. That's how we formulate this problem, where I would say, so my first assumption here you could think of is, consider, if not assumption, just consider a scenario where my goal is to put a, the brightness remains constant for that particular pixel as I move from one frame to the other, but within the point remains within the neighborhood of the xy. Suppose if I consider here This point has moved when I come to the next image, but within some neighborhood vicinity itself, it is there. So then what is the constraint that I am going to keep here is I of x plus u. It has moved to a location x plus u. So the displacement in x direction is u. Displacement in y direction is v. I am in the t plus 1th frame here. This has to be equal to I of x comma u comma, sorry, I of x comma y comma t. So there is a teeth frame here. This is a teeth frame. You could see here. This is a t plus 1th frame here. Now, what I am putting here is, now there is a motion of u in the x direction, v in the y direction. Since I am saying that the intensity of that particular pixel would remain constant, and that is how I would like to find out a matching for this point, I am writing it as I of x comma y comma t. In the teeth frame, the intensity at a location of indexed by x comma y. In the t plus 1th frame, it is just moving by values of x comma y. I could find out by moving u distance in x and v direction in y. Now the job for you by the next class is to solve this equation and arrive at this. This would be the final equation that you would be getting there. And now think about these questions also. Is there a unique solution for this? Or are there multiple solutions for it? So I'm going to give you this slide also, or else you could also make a note of it. This is what you solve this equation. So what we are telling you is this u and v are small, okay, and the motion from t to t plus 1 is also small, you consider. Now do a Taylor series expansion of I of x plus u y plus v t plus 1 over by starting with I of x y comma t and solve it. I'm giving you the final answer also, so you fill in the blanks in between and compute that. And now I leave you with solving this question, deriving this expression, starting from this brightness constancy constraint. Okay. And then you also try to answer by the next class, how many unknowns and equations per pixel are there in this problem? Is the solution unique here or not? Okay. That's something I would leave you here with.
Yes, sir. Could you repeat it once?
Yeah. See, I am assuming the brightness of the pixels would remain same as I move from, despite moving from one frame to the other, except that the pixel has got a displacement from while moving from the first frame to the second frame. That's the basic assumption, or what it means by brightness constancy constraint. So now I am formulating it as, for example, so here earlier I am writing each image pixel as I of x comma y. Now I also have a time frame here. The third dimension is also there. So that's why I have here t, here I have t plus 1. Okay, I have x comma y of t plus 1, I have one image. This is t plus 1th frame here, and intensities are indexed by x comma y. This is tth frame, again intensities are indexed by x comma y. Now since we are saying that this pixel has moved, this intensity, that the object has moved, that means the pixel, this intensity maps to an intensity which is there in the neighborhood. So where it has moved, it can move in both x and y. The motion in the displacement in x is u, the displacement in y is v. So what we are now trying to solve here is I of x comma y comma t is equal to I of x plus u comma y plus v comma t plus 1. So maybe I would give few more hints as well here. So what are the unknowns here that you need to compute?
I think the displacement u and v.
That's right. That's right. At each pixel, you need to compute u and v. How many equations are there here? How many equations do you see in this slide?
Only one.
Only one equation is there. There are in fact multiple solutions. Okay, so I anyway answered this question myself, but still what I still give you as an exercise is to arrive at this, where your gradient of I is equal to, okay, ix comma iy, this vector. You make a note of it, and you try to, I wrote it as a dot product of it. So the multiple solutions I want you to draw. For example, you consider in an image there is an edge there. For example, how you could have multiple solutions that could satisfy this equation. You try to draw it geometrically, and also from the equation you try to interpret the same. And once you draw it geometrically, you get into a very nice further interpretations of it, which would help you to understand it very clearly. Let me stop here and see you in the next class.